Just put a heading radioactive decay. I want you to write few lines on that as well. What is it exactly? Spontaneous integration, disintegration of nucleus to form some stable nucleus. This is the same definition as this reaction is also called as radioactivity. But there is another name for that, radioactive decay. So resulting in the emission of alpha, beta, and gamma radiation. I want you to just write the definition and then we will come back to the some numericals related to that as well. Yes, Manu, did you copy that?
Yes, sir.
Okay. Now let's see the question again. Now remember one thing. Sometime, as I told you previously, you've been asked number of atoms. Sometime you've been asked count rate. Sometime you will ask activity. It all means the same. So if the question is asked, remember, sometimes in your course, the minus sign is also shown here. What is the meant by minus sign? That the value is reducing. Okay. Now, if you see the formula here, it's the same formula what I have told you, but with a different sign conventions. This delta n means amount, or sometime we can ask, like we can say that amount, you can say amount of the decayed element or whatever. This A means the activity of the sample, or you can say amount. This means number of decayed element, and T means the time interval. And that will give you the amount. It's the same formula, no difference at all. So basically, I'll show you the numerical ways, then you will understand it more. So activity of a sample is measured in the becquerels, okay? The activity of one BQ is equal to 1 decay per second. It's the same thing as we will talk about number of atoms or something like this. Here we called it becquerels, okay? Now let's see it. If you see this question, how to use this formula, let's see. They say radium is a radioactive element first discovered by Marie and Pierre Curie. They used the radiation emitter from radium-226 to define a unit called Curie, which defined as the 1 gram of radium. It was found that 1 gram of sample of radium, 2.2 into 10 to the power 12 atoms decayed in 1 minute. Now, what is what? Another sample contains this number of radium. Atoms have an activity 12 Ci. Determine the value of 1 Curie. Now, what exactly they are asking you? 1 Curie and what exactly? And they say determine the decayed constant of the radium. Now, first important thing is number of atoms decayed, delta n is given, which is 2.22 into 10 to the power 12. And time is given, which is 1 minute, and you can convert it into seconds. So how to find out the activity equation? It says that A is equal to number of decayed atoms divided by the total time. So for you, this is a new formula now to find out in terms of activity. So what is the number of decayed atoms? 2.2 into 10 raised to the power 12, and time is 60. So what is the activity here?
3.7 times 10 to the power 10.
And what is the unit for that? Decays per second. It means in each second, the decays will be decay per second, this much. So technically speaking, this is not any particular formula or any typical formula. It's just number of atoms decays divided by time. Understood? Or any problem in this?
Understood.
Very good. Okay, now the next part, which says determine the decay constant. Now, how to find out decay constant? The value is very simple. Now, number of atoms, we already know that. How many are there? And A means the number of element decays. So remember that A divided by N, where A is basically decay per second divided by the total number. This will always be a constant quantity, which is given here as lambda. So basically, when you do that, you got 4.44 into 10 raised to power 11 divided by 3.2 into 10 raised to power 22. The value comes as 1.388 into 10 raised to power minus 11 second inverse. The decay constant for the radium is 1.4 into 10 raised to the power minus 11 second inverse. Now, this value is constant for different materials. For radium, this is the value. Maybe for some other element, the value will be different. For some other element, the value will be totally different. So for all elements, value will be different. So what formula we have studied for this today? Activities is equal to number of decay atoms divided by time. And then once you find out, we found out that number of activities equal to constant value multiplied by the number of atoms. Or in other words, lambda will be equal to A divided by N. The unit of lambda we found out is second inverse. If you remember, what do we call second inverse, by the way? In one chapter in IGCSE, we have learned what 1 by second means. Yes, Manu?
Frequency?
Frequency. So technically speaking, this is the frequency. How frequent the decay goes. So this is the frequency of the decay. How frequent the decay of the radium element is. And this is constant for a specific element. Understand?
Yes.
Okay, now let's see. Let's quickly test ourselves. We see how good we are now to understand this. First point, a radioactive decay is a phenomena that revolutionized our understanding of atomic physics. A list of words is provided below. Predictable, infinite, random, or dangerous. What is it? Is it?
Random?
It's a random one, I believe too. Because random means we can't just predict it. So let's see. Yeah, it's a random. Definitely it's a random one because it's impossible to predict. We can't predict it. Okay, the next one. The decay constant of a radioactive isotope is used to calculate its half-life. Define decay constant. Second is half-life. What is half-life? Quickly.
The time taken for the activity to divide by half, or the count rate?
The number of atoms to become half of the quantity or number of
Yeah.
activities to become half. And how to define decay constant?
Decay constant is activity, a total number of particles over the total time taken.
Yeah, so number of particles or number of activities decayed or number of decay particles per unit time. So division, I mean, ratio between uh, number of particle decay per second divided by the total number of particles. Is that the one? Yeah, it is the one. See, the probability that an individual nucleus will decay per second divided by per unit of time. Decay constant. So probability that an individual nucleus will decay per second divided by per unit time. So they are giving you the probability of this. And the second one is time. Yes, Manur, any question?
No, sir.
Okay, let's take another one quickly. Now, this one is good. A carbon dating is a method used by scientists to estimate the age of organic material. The reliability of a carbon dating depends on the age of a sample being dated. Place a tick in one of the box below to select the range of ages for which an age determined by the carbon dating would be reliable. What do you think?
1,000 to 40,000?
Let's see. Oh, good. Great. Remember that one we can find out, but as it becomes older and older, then the reliability on the solution of the carbon dating will be gets lower and lower. Sample X contain 1.25 into 10 to the power 26 radioactive nuclei. The half-life of a sample X is 1500 years. Calculate the number of nuclei remaining after 4500 years. Can you quickly do that? It's a half-life question. What is the formula for this, Manu?
Number of particles over 2 to the power of n.
Yeah. So basically, number of particles, which is given as okay. Calculate the number of remaining. So they are asking you the remaining ones, which are here. So number of particles. The sample contains. Okay. So basically, number of particle for the time being is 1.25 into 10 raised to the power 26 divided by 2 raised to the power n, right? And
Yeah.
basically, half life is already given to you, which is 1500. So how many half lives you will have it? 4500 divided by 1500. So what is it?
3.
3. So you can place 3 here. So how much is the answer?
1.5 times 10 to the power of 25.
Very simple. Let's check it out. Yeah, it's 1.56 10 to the power 25. Right? Okay, next. Now I want you to try this. A protactinium has a half-life of 70 seconds. A sample of containing 0.5 moles of whatever it is prepared and monitored over a period of a time. Determine the percentage of protactinium remaining after 210 seconds. Now they are giving you answer, value in moles, so you're getting value in moles.
0.063.
But they are asking you a percentage. So what is it? That value which you just found out is the amount left, right?
Yeah.
So you divided by 0.5 and multiplied by 100 will give you a percentage. So what is the answer?
79.
12.5 actually. But why is this? What is the value you just found out, by the way?
0.063.
0.063, right? Divided by 0.5 and then multiplied by 100. So what is the value?
It's 12.6.
12.6. So that is what the percentage is. It means that after 3 half-lives, your material, which is 0.5 moles, will be just left with only 12.5% of the total amount. That's what it means. It means that in the third half-life, once the third half-life will finish, your total material or your total number of moles or grams, whatever it is, only 12.5% of the total amount left behind. It means how much is actually decayed? What percentage will actually be decayed already after third half-life? Yes, Manu.
It will be 88%.
Yeah, something like 88 or 87.4%, something like this. So understood?
Yeah.
Good. Okay, now let's come to the point which actually I want you to take. I want you to understand. We have done this nuclear fission and fusion reaction. Did we do the comparison of both of them?
Mm,
No, we didn't, right? But we have done
yeah.
fusion reaction. So I want you to put a heading of fission and fusion reaction, and then we'll do the contrast of both of them. Yes, Manu. What happened in fission reaction? In fission reaction,
Fission is when one larger unstable nucleus dissolves or becomes two small nucleus.
with lots of energy release, right? So you can say that
Yeah.
splitting of a big nucleus into its daughter nucleus or some smaller nucleus along with lots of energy is called as fission reaction. So disintegration of a bigger nucleus into smaller nuclei is called as fission reaction. And what about in fusion reaction, Manu?
Fusion is when two small nuclei became one big nucleus.
So fuse together to form one big nucleus. Then the second difference, or you can say the major difference is the equation. I want you to write the equation for that. It says neutron, then uranium 23592. Then it will become krypton. Let me just write it properly so that you will be able to actually.
I've written this already. The equation.
Then you write it, but we are now writing this equation in the contrast quickly so that we will finish off this topic, right? Manu, what was written on the krypton? Do you remember that or forgot actually?
I think it
No.
was 91.
Okay, that's fine. Yeah, yes, fine. Okay. The second difference will be about you write the equation here, right? What about in fusion? In fusion, you will write that equation where two hydrogen fuse to give you helium. Write this equation on the other side. Then the second point. What is the major difference? What reaction is a fusion reaction? Endothermic or exothermic? Yes, Manu.
Fusion reaction is endothermic.
Because you have to provide energy to make the fusion happen because two smaller nuclei combine to give a bigger one. So you need to provide extra amount of energy. So you can just write here in this that the amount of energy that is released will be less than the amount of energy which is given. On the other side, fission reaction, you can say that it's the exothermic reaction because the energy provided will be less than the energy released. What is the third major difference between a fission and a fusion reaction?
Fusion only happens in like the sun.
So you can say that there are conditions, specific condition requirements for the fusion reaction to happen that is very high pressure and high temperature, which is only available on sun. For fusion reaction, there is no such special conditions required. So high pressure, high temperature is required for fusion reaction to happen, which is only possible at sun. So now you understood the difference between nuclear fission and fusion. We have done this all right. Now let's come
Yeah.
to the equation, the one I actually want you to come on that. First of all, here, first of all, I will give you a quick concept of what we have studied already, and then there is a new concept which called matter and antimatter, which actually we have to provide you here as well. The first thing is what happened. Just put alpha decay. Alpha decay. Now, Manur, when we study alpha decay, we have seen that in alpha decay thing or in alpha, what alpha is basically, alpha is a helium nucleus with mass, sorry, with the proton number is equal to 4 and mass number is equal to 4. Or you can say proton number equal to 2 and nucleon number equal to 4. So remember that, let's suppose this is your X. Let's suppose any element we have it. Here I am writing A and on top I am writing Z, where A is your atomic number or proton number and Z is your nucleon number. When helium nucleus get out of this material, what will happen? What do you think of it? The proton number will be reduced by 2 units and nucleon number will be reduced by 4 units. Okay. So first write down, don't write this X or Y, just write it down. When alpha decay happened from an element, proton number of an element is reduced by 2 units. Proton number will be reduced by 2 units and nucleon numbers will be reduced by 4 units. Okay. So first write down when alpha decayed happened from an element, proton number of an element, proton number will be reduced by 2 units and nucleon numbers will be reduced by 2 units and nucleon numbers will be reduced by 2 units. So and nucleon numbers will be reduced by and the nucleon numbers will be reduced by 4 units, and the nucleon numbers will be reduced by 4 numbers. I want you to write this X sign along with that. This is proton number, this is nucleon number. When helium nucleus is removed from here, so technically speaking, your X, Z is removed by 2 and A will be removed by 4. I want you to write this equation. So Manur, any problem in this?
No, sir.
Okay. Did you write it?
Yes.
Okay. Now let's see some examples for this. There are some examples which are actually being done for you here. Now check this out. Both in the numeric form, I mean, both in the uh, symbolic form and in the English form. Uranium 235, when there is alpha decay, it's changing into thurium, a new element. That is the equation of it. Uranium 92 235, when alpha is decayed from here, it converts into thurium. Now check this out. 92 is converted to 90 and 235 is converted into 231. Now you don't need to memorize the element name, but what you need to memorize is these things, the rule that once the alpha particles are removed, the mass number is reduced by 4 units and atomic number is reduced by 2 units. I want you to write these equations. So Manur, what exactly is changed while the there is a change in mass atomic number and the mass number? If I'm asking you in form of number of neutrons, number of protons, or number of electrons.
The neutrons stay the same, but the protons decrease by 2.
Okay. So if protons are decreased by 2, what about the number of neutron as well?
They would also decrease by 2.
Yeah. So basically,
And
So
yeah,
number of neutrons are also reduced, but number of proton will remain the same. I mean, number of proton are reduced by 2 and number of neutrons are reduced by 2 as well. That is the reason, because here it's only reduced by 2. Here, the number of neutrons are also reduced by 2. So if I ask you the difference between uranium and thorium in this particular equation, you will say that, can you tell me what is the total number of proton, number of neutron in uranium 92 to 35 quickly?
143.
143. That is number of neutron. And what about in thorium now?
That's 141.
So what is the difference?
2 neutrons.
2 neutrons. So it means that 2 neutrons less than the uranium it has. Proton is just 2. Okay. So understood?
So does that mean that electron number will also decrease?
But electron is just, you can say why electrons are reduced, because they become a charged particle now. Yeah, if you ask, for example, me, then definitely there are 2 electrons also reduced. So if 2 electrons are reduced, means the charge become positive. So 2 extra, you can say 2 electrons if removed. So what is the total electrons you have it? 90?
It's 90.
Yeah.
Yeah.
But they normally don't ask electrons because electrons is nothing to do with the mass. You know, when you're talking about the mass thing, you will never find electrons anywhere. It's only related to the charge, because electron is sort of a massless entity. You never ever heard. That's the reason we called it a proton number. You never called it atomic number anymore in this. If you read this all, you will find out that they are talking about the total mass, before and after. It will not, they will not ask you, they will not even care what electron is. But as far as charge is concerned, yes, there is a change in charge. Okay, now there are further equations in here. And I want you to write this equation as well. Radium 22388 will convert it into radon 86 219 along with the helium. And the second one is, yeah, here another example, americium is converted into neptunium with along with the alpha decay. This now, if you check this out here, the mass on the left hand side is 243. They didn't talk about this proton anyway. They are talking about the mass. But on the other side, it's 239 plus 4 will give you the mass on the right hand side. So remember that the mass and the proton number, they should be balanced on both the sides. So 95 on the left hand side, on the right hand side, 93 plus 2, which gives you the atomic number, or you can say proton number. Also write this one as well, please. Conservation of charge and all this. Along with the alpha particle, sometimes we do have a gamma photon emission as well, but it doesn't make any effect because gamma radiation is massless as well as chargeless. So it doesn't change anything in the material properties, or you can say it doesn't change its proton number or either its mass number. Okay.
Yes, sir, I'm done.
Okay. Now I'm not giving any questions or any equations related to gamma particle. Can you tell me why I'm saying this?
Gamma is just energy.
Actually, a gamma particle doesn't do anything, any contribution in changing of atomic number or mass number, anything. They are just, or always remember, whenever there will be a gamma particle, it will be along with either a alpha particle decay or beta particle decay. Okay, they are not going
Yes.
out alone because it doesn't affect anything, either proton number or a mass number in this. Okay, now the major things comes in. That is the beta decay, which actually I wanted to talk about. Now, what is beta decay? That's where the point started. Applications, half-life, we have done this. Okay, nuclear stability graph, decay equations. That's where actually I wanted to come on. Now remember that when you're talking about decays, then the major thing now comes up here is a beta decay, which actually I wanted to talk about. Now remember that beta decays, or you can say when electron is removed in form of beta, there are two type of decays. One decay is called as beta minus, and the other decay is called as beta plus. So first of all, I want you to put a heading beta decay. Now check this out. If you write it down, just put the pen down and listen to me very carefully at this one. Now, if you check this out, if it's a beta negative, what does it mean? Your proton number will be actually increased by 1. Banur, if your atomic number or proton number is increased by 1, what does it mean? What is actually increasing?
The protons,
Protons are increasing. But question is where this proton is coming from. Does it come from somewhere?
the neutron.
Yes. What actually happening? Remember then when there is a beta negative decay, one of the neutron is converted into a proton. So technically speaking, the A value remains the same because A value is a sum of protons as well as neutrons. So as far as sum of neutron and protons are concerned, they will be same. But if I ask you what is the number of neutron now, then number of neutron will be reduced while there is a beta negative emission because neutron is converted into protons. That's the first point. Now you see a very unique sort of sign. Now, what is this? That's what the point is. Now, at this point, we have a concept of matter antimatter. Okay, the concept is matter and antimatter. One of the neutron in the nucleus changing into proton, and a beta negative, an electron, and anti-neutron is released. Now, this is very important thing. This is called antimatter. Remember that till now we have only studied three major elements of an atom, that is proton, neutron, and electron. But remember that there are approximately 92, 93 further tiny particles inside an atom which are already discovered. So this is one of them. And this is called the Now remember that what we believe, scientists believe that every single thing, whatever in this universe, will always existed in the pairs. Like as far as our Muslims are concerned, we believe that there is dunya, there is this world, and there is world after. So this is also in couples. So what we believe is that if one neutron in the nucleus changing into proton, so it means that if one neutron it is converted into proton, it means that to compensate this, what you can say, to compensate that, there is one anti neutrino is also produced or released. This is same as the neutron, but it's the anti of neutron. It is just to balance the effect of the neutron, which actually changed into proton. Okay, it is nothing but to compensate the loss of neutron into proton. Okay, so what happened in this? One of the neutron nucleus changing into proton, and when the beta negative particle released, anti-neutrino is also released with this. And this is a sign of anti-neutrino, which is actually an anti-particle of a neutron. So you will find out that in every single case, there is an anti-particle of this. You will find out further when you go further that if there is a proton, there is an anti-proton as well. If there is a neutron, there is an anti-neutrino as well. So there you will reach to a point where you will find out that to the anti of the neutron, you will have an anti-neutrino, which have no mass, nothing. It will not affect anything. Till IGCSE, we didn't teach this one. But at this level, remember that one neutron converted into proton. So to compensate the effect on the right hand side, there is an anti-neutrino which will be released as well. Manur, any question in this?
No, sir.
So what exactly happened if I ask you as far as number of proton is concerned? So number of proton is increased by 1 and number of neutron will be reduced by 1. Okay. I want you to quickly write that and write this equation. This is one of the major equation and put a small heading beta negative emission because there will be a beta positive emission. Right at this is called anti-neutrino. Yes, Manu, did you complete that?
Yes.
Okay. So now this is your beta negative emission, right? Now there is an emission called beta plus emission. Now what is happening in beta plus emission? In the previous one, what happened? Neutron is converted into what? Proton. In that case, your proton will be converted into neutrons. Previously, when neutron converted into proton, you will have an anti-neutron particle that is anti-neutrino. In this case, because proton is converted into neutron, so instead of anti-neutrino, you will have a neutrino component. Or in other words, now check this out. One thing which we missed in the top one, electron is also in beta emission, an electron, an anti-neutrino is actually released. So did you write this electron thing as well?
Yes.
In that case, electron and anti-neutron released in beta plus because proton is converted into neutron. So anti-proton is what? Positron. And previously it was anti-neutron. Here it's just neutrino. They were released. And both are like electrons never show here because the reason I have already told you they are massless entities. But these ones we have to show it to show the compensation of the particles which are converted. In this case, it's positive charge which is converted. It's positive charge proton which converted into neutrons. We will continue this one in the next class. Okay, but till now, did you understand or any question?
No question, sir. I understand.
Okay. So tomorrow, I think tomorrow we have a class. Oh, no, I don't think so. On Monday now we have a.
Yeah,
So from Monday
yeah,
we have as usual our classes. Our schedule will be the old one. Okay.
yeah.
The previous one. So hope to see you on Monday then. See you same time, inshallah. Bye.